Good day, everyone, and welcome to our first Lightbend webinar of 2019, titled Akka and Kubernetes, Reactive from Code to Cloud. My name is Oliver White, Chief Storyteller and MC at Lightbend, and I'm happy to welcome a special guest to our webinar program today, Fabio Tiriticco. Fabio is a Scala and Akka engineer, conference speaker, and the leader of Reactive Amsterdam, which at over 2,500 members may be the largest reactive user group in the world. While I introduce today's session and let everyone get settled in, I'd like to ask you, our dear audience, a quick poll question about Kubernetes industry adoption and acceptance. We'd like to know, how do you plan to run and deploy your services 6 months from now? If you're joining us today, then I'm willing to guess that either Akka, Kubernetes, or both technologies are of high interest to you. And for good reason. One of the best benefits of using Kubernetes is that, like Akka at the code level, does a lot of heavy lifting for you regarding container orchestration. You don't need to worry about resilience, scalability, or wiring together a lot of things that normally would make an operations or DevOps engineer take a bit of a moment to pause and wonder if everything is correct. What we'll learn more about today is how Akka is actually the perfect companion for Kubernetes, providing the application-level requirements to successfully deploy and manage cloud-native services with technologies built specifically for cloud-native infrastructure, such as Kubernetes. After all, many of us have learned the hard way that we can't simply take our old Java EE6 monolith, throw it into a Kubernetes pod, and count on everything working out. The reason why this doesn't work well is something that Fabio will go into detail describing later. Now, if you break it all down to just one concept, it's this. Akka provides you with stateful, data-driven services, meaning each service owns its own data and is backed by an event source. And Kubernetes allows you to run these services as if they're stateless, meaning less infrastructure considerations and overhead. In general, it's a match made in heaven. It's all scalable, resilient, and reactive all the way from code to cloud. All right, thanks for your votes, folks. Just a little bit of housekeeping before we hand it over to Fabio. As always, today's webinar is made possible only by people like you encouraging your company to become one of Lightbend's hundreds of happy customers, like our fabulous client Walmart, who is looking for talented folks with experience in Scala, Akka, and Apache Spark to join their labs ecosystem team in sunny Sunnyvale, California. You can find out more about this position and other open positions with Lightbend customers and innovators on our newly designed website under the About tab. Of course, today's webinar is being recorded and it will be shared with you next week. If you have questions, feel free to add them to the GoToWebinar control panel, and we'll see if we can get around to them in the Q&A part of today's session. If you are an existing Lightbend subscriber, then you know that you can have unlimited access to our expert engineers through the customer portal, where you can log in and ask any technical questions about Akka, Kubernetes, Spark, Scala, Play, Logem, etc., as well as architectural how-tos, best practices, and what-ifs. All right, thanks for listening. That's all from me. Now, I'd love to hand it over to Fabio. Fabio, thank you very much for joining us today, my friend.
Hi, thanks, Oliver, and hello, everybody. I'm really glad you're here for this webinar. I'll just say a couple more words about myself. My handle on the internet is TicoFab. It's pretty much everywhere. It's on LinkedIn, Twitter, what have you. And I work as a Scala and Akka consultant based in the Netherlands. And a couple of fun facts about myself. I once cycled all the way from Amsterdam to Rome, my hometown in Italy. And I used to have a side business as a street food business, and I don't have that anymore. But if it looks like fun, but it's a ton of work. And so if any of you listener is thinking about such a business, please come talk to me first. But maybe more related to the topics of tonight's webinar, I am also the organizer of the Reactive Amsterdam meetup. We started about 3.5 years ago. And we really are in love with everything reactive, from reactive programming to reactive system designs, and we cover a wealth of technologies. And in fact, due to my involvement with the community, I was able to realize that the reactive community and the Kubernetes community, even though they are after the same goal, which is designing and building distributed reactive systems, well, their terminologies their vocabularies are quite different. So in the reactive community, we talk a lot about actors or reactive programming, asynchronous messaging, streaming, while in the Kubernetes community, there's a lot of talking about Docker and resource provisioning, service discovery and microservices and all that. So I settled out to see, well, what if we combine these two worlds? How can we get the best of them? And the outline of this talk tonight is we'll first glance over the reactive principles, and then Akka and Kubernetes. Those will be a quick overviews to be all on the same page. And then we'll dive right into what happens when Akka and Kubernetes are combined. We'll look at a couple of elasticity and resilience use cases before we get to our conclusions. So reactive principles. I assume most of you have seen this already. The Reactive Manifesto is a description of high-level principles, really, created in 2013 by Jonas Bonner and a few others. Basically, what they did is they looked at the architectures that support massive systems such as Facebook or Twitter and sort of summarized their essential traits. What this manifesto tells us is that we strive to build elastic and resilient systems based on a message-driven architecture in order to guarantee our users a responsive experience at all times, even in case of failures or load spikes. And when I say users, of course, I don't only mean humans, but a user of our service could be very well another service, so user in general. In this talk, we'll mostly look at elasticity and resilience. So, elasticity. Once we were thinking more in terms of scaling up, that is making our machines more powerful, faster, but that approach has reached its limits in the last 10 years or so. And that is due to the speed of light and heat dissipation issues. So instead, the world resorted to making things parallel. Instead of having bigger machines, we will have more machines, which results in challenges in parallelizing things and maybe collecting results and things like that. In other words, elasticity today means we need to distribute things and execute tasks concurrently. Now, when the key to elasticity is distribution, the key to distribution is location transparency. And let me just introduce this concept with a simple example. Let's say Oliver is in New York and he wants to send me an email. Well, to him, it doesn't matter whether I am in Siberia or in Australia, or if I am in the same building where he is, because all he needs to have is my email address, and I will get his email anyway. So this is the link between being message-driven that enables location transparency, and location transparency is key to distribution because, coming to the IT world, if I don't need to know the physical location of a recipient, I am able to transparently move, say, a worker from one node to another, where it can use more resources, for instance. Or if I have some code that invokes a service and the system has location transparency, then I can add or remove servers as needed without altering the code that invokes that service. So that's for a high-level description of elasticity, which is really the ability to add resources as needed, but also to remove them as needed. In this cloud-driven era, we really pay for what we use, and we only want to use the right amount at every time. How about resilience? Well, there's an important distinction here that needs to be made, that is fault tolerance versus resilience. What's the difference between them? Fault tolerant is defined as a fault-tolerant component is hit but keeps going, possibly with reduced functionality. And the best image I could find to sort of show this concept is with this guy. Do you remember this guy? This is the ending scene of the first Terminator movie. And, oh, man, the good guys throw everything they have at the bad guy, but he just keeps crawling. And even when he loses his legs, it just pulls himself forward. So I would totally say this guy is very, very fault tolerant. And what about resilience instead? We can define it as, upon failure, a resilient component is able to jump back to a fully functional fresh state. And again, again from the Terminator series, this is the guy from Terminator 2. And when he's grounded, maybe, yeah, because there's too many holes or something, then these wounds, they magically heal. And after a little bit, he's able to jump back fresh, new, like nothing had happened. And so this is the difference between fault tolerance and resilience that we need to keep in mind. Now, after having introduced these high-level principles, what is Akka then? How does it help us towards these two goals? Well, from the reactive principles, we can derive some reactive design patterns, and Akka provides us with some reactive building blocks to actually implement these design patterns on an application level. And Akka runs on a JVM, so on a Java Virtual Machine. And how does Akka help us in terms of location transparency? Well, Akka's building blocks are actors. And actors, you can think of them as basic unit of computation that contain its own business logic and its own state. So if I have one actor, maybe its internal state, its name, it's John. And the crucial thing here is that actors can only communicate by asynchronous messaging. So if I have another actor, and this other actor needs to know what is the name of the first actor, the only way to access it is ask. Actor 2 can send a message to actor 1 asking what is your name, to which actor 1 will respond, John. And this is crucial in terms of location transparency, because if I have this thing running on a single JVM, well, I can easily move one actor to another different JVM, and the mechanics of their communication will stay exactly the same, just like my email example from earlier on. So actors, they're essential in that they provide state isolation and location transparency. And building on top of that, Akka lets us connect multiple JVMs, each one of them with their actors running in it, and exchange messages transparently. And Akka cluster and Akka cluster sharding in the bottom left, those are the two models that I suggest you to look at to achieve this. And in this kind of situation, elasticity is achieved because if I need more processing power, I can spin up a new node somewhere and move some of the actors there to use those new resources, and the mechanics of my entire system won't change. And as well with removing nodes. So this is the way Akka helps us with elasticity. And how about resilience? Well, every actor is created by a supervisor to whom failure handling is delegated. If something goes wrong into the actor, the supervisor will take care of it. And benefits of this are that, well, business logic and failure handling are now clearly decoupled. So my business logic stays clean and lightweight. And as a side effect, it's also easier to test. And the supervisor has flexible ways to react to the failure. So it might restart an actor, it might stop it forever, it might resume it. It depends on the kind of failure that happens inside the actor. And also this guarantees isolation. So we don't have cascade failures to other parts of our system. And in practice, what does it look like? This is our friend from earlier on, and let's say that you want to code a terminator. I don't think it's a good idea, but unfortunately, I'm positive that someone on this planet is trying to do that. But anyway, let's say you want to code it using Java without Akka. Then most likely you will have a T800 instance, and your code in it will look like something like this. You will try and walk, but you know that things can go wrong, so you might want to catch an out of legs exception right there. And when that happens, you might want to update your internal state, because your legs available is obviously false now, and then provide some alternative ways of moving. And I think we've all been there, and it gets messy from there. Lots of things can go wrong, and it's very difficult to track the state and to reconstruct it. How about the Akka world instead? Now, this guy, the T1000, is an actor now, and the code inside this actor will be as simple as walk. Now, if something goes wrong, this actor has a supervisor, the Skynet actor right there, and inside the Skynet supervisor, we'll have something like this, where if we detect that there's the too many holes exception being thrown, then we can decide to restart our actor, and it will spin up fresh as a daisy. Code is simpler and better separated, and well, when one actor is restarted, you probably want to be able to recover your state. Like, what was my name again? And this is where state management solutions come in, like event sourcing. We don't have time to discuss those, but just know that Akka got you covered there as well. So we've seen how Akka helps us with this elasticity and resilience at an application level. Now, how about Kubernetes? How does it help towards this goal? First of all, what is Kubernetes? For me, the simplest way to think about it is like a waiter. If you have a menu, and your menu consists of services that you have packaged into a Docker container and uploaded in some container registry where they are available to Kubernetes, then you have your menu right there. And you can compile an order to give to Kubernetes saying, oh, I want to have 1 instance of the auth service. I want to have 4 instances of the picture resizer service, because we know we're going to use that a lot. And I want 2 instances of the uploader service, for instance. And Kubernetes will make sure that you get it. Each of these instances will be cabled in a sense that we'll have networking enabled and will be reachable by all the others. All the piping is there for you. And Kubernetes goes further than that even. So for instance, instead of asking for a static 4 instances of the picture resizer service, I could change my order into, I want a minimum of 2 instances up to a maximum of 8 instances based on how hungry I am. And now maybe you might be wondering how is the waiter supposed to know when you're more hungry, when you need more food or less food? Well, we'll get to that in a minute. But so this already hints at Kubernetes being able to scale up and down our services. Let's look at location transparency, the same concept, but then in the Kubernetes world. So at the bottom of everything, there's virtual machines. Kubernetes works with virtual machines like EC2 instances on AWS, for instance. And the basic computational unit in Kubernetes is a pod. And for our talk, a pod contains a Docker image. So in our case, each pod contains a JVM. And the thing is that these pods have labels. So in our case, we labeled name A, or pod 2 is labeled name B. And the thing is, we don't need to know anymore the IP addresses of those virtual machines. We can use the pod labels, or Kubernetes even offers us a DNS service to reach them. And so you, as a developer, don't need to know in which virtual machines your processes and your actors will be running. Inside each pod, we will have our JVMs and conversely our actors. And they will be able to message each other, like we've seen earlier, between different pods, without you knowing even on which virtual machines these actors are running. Could be the same, could be another one. It's not something that you have to worry about. And so that's location transparency in Kubernetes. And this goes on to the concept of elasticity in Kubernetes. The way it is most commonly referred to is that, let's say you have 2 services running, on your Kubernetes cluster, a front-end service and a back-end service. And the front-end service only has one pod running, but the back-end service has multiple pods. Well, then you can use a load balancer provided to you by Kubernetes so that the front-end service can only talk to the load balancer without being aware of how many instances of back-end services are there. If Kubernetes sees that that we need more instances of the backend service, it will just spin up a new one right there or remove one. And this is where, remember earlier I was mentioning the waiter that needs to know when we are more hungry for and we need more food, or in our case, more processing power. Well, Kubernetes has a very simple way to detect that, which is it will just look at the CPU usage of your processes or memory usages as well. And when it sees that they are going high and reaching the limit, it will spin up a new one. So that's a pretty basic criteria, but it will meet still the needs for some people and some problems. How about resilience in Kubernetes? Well, given the same situation, let's see, for instance, one of the pods in the backend service might crash. And Kubernetes will detect that and will immediately remove it from the load balancer so that the traffic won't be routed to it anymore. It will then completely eliminate it, and if needed, restart it fresh. So as simple as that. This is the concept of resilience in Kubernetes, and all this has been transparently done to the front-end service. It didn't realize that something was happening in the back-end service. Now that we have introduced these concepts in these two worlds, then we can see what happens when we combine them and how can we combine them. Well, if we run Akka on Kubernetes, then the stack will look more or less like this. At the bottom, we will have virtual machines inside which our pods will be running, one or more per virtual machines. And in each pod, we will have JVMs running that are all brought together by the Akka cluster module. And inside our JVMs, we'll have our actors that then will be able to communicate with each other. And so when Kubernetes is already helping us with resource provisioning, spinning our nodes up and down. But not only that, Kubernetes can also help us with cluster formation. So let's say that you have these three nodes, they are up, and they are named differently, Akka node 1, Akka node 2, but they have one label. You can give as many labels as you want, and one label is in common to all of them. It's the one in red, my cluster. What these nodes can do once they have been brought up is they can talk to the Kubernetes API. Kubernetes has this manager, roughly it exposes some API that you can talk to. And so each of these nodes can ask to the Kubernetes API if other nodes like him share the same label. And Kubernetes API will realize all that and make sure that they are aware of each other. This is done by the Akka cluster bootstrap module, so I encourage you to give a look at that as well. And once the cluster is ready, maybe you want to spin up another node because we need to process more traffic or something. Well, this new node, again, will talk to the Kubernetes API and join the rest of the cluster. This way, if you used Akka cluster before, you remember that we had to specify a set of seed nodes that every other node in the cluster had to know how to reach. And we don't need that anymore if we rely on the Kubernetes API. So that's, again, one step more to independence and elasticity there. So in combination of Akka and Kubernetes, let's look at a couple of elasticity use cases. A simple one, distributed workload. We want to keep track of the processing rate according to some custom metrics, very specific to our own business. Now, how would we go about that? if we delegate all our elasticity needs to Kubernetes, that is to the infrastructure level, here we really are reasoning at the abstraction level of a pod, because Kubernetes doesn't know anything about what's going on inside a pod. All it knows is a Docker container. And so what we'll do is we'll have a load balancer typically in front of a set of workers, and the master pod will be able to hand off work to them via the load balancer, just like we've seen before. And the load balancer is able to distribute load in a couple of very, very basic ways, and the workers should somehow tell back to the master the results of their work, and we need to know, the master wants to know exactly which worker did what and things, how long it took, things like that. The default way to do this is using HTTP and just waiting for the response to come. We could do other things, but yeah, this is the default way most people do that, and it's not very flexible at all. How about if we introduce some collaboration between the application level and the infrastructure level? So now we are reasoning at the abstraction level of actors within our application. And something I didn't mention about actors is that they shine at concurrency, executing things in parallel. So you know that already performance will be great, but also that Akka provides a dynamic routing components to distribute messages across actors. And routing rules can be fine-tuned in many ways, such as round-robin way, or a random way, or a balancing way. Akka tries to balance work between the workers, and so on. So in this case, you can see the master embeds this router. And all communication now happens via actor messaging, which is much better than HTTP from a performance standpoint, but also makes collecting results, so communication back and forth, a lot easier. It's just about sending a message back to the master. So if we use Kubernetes to leverage this, then we will have a situation like that, where some workers run in a pod, some workers run in another pod. There will be one pod that contains our master actor, and maybe most importantly of it all, because now we are taking care of the scaling logic directly inside our application, we can also have finer control to how we add and remove nodes based on our own business logic. Via the Kubernetes API, again, the master can collect all the results, process them, have some calculation that really depends on your own business logic, and decide to spin up new nodes or remove them without having the constraint of CPU usage or memory usage as the only criteria. And I think this is way more flexible. You have less infrastructure overhead, and in fact, with a friend, we created an example that does exactly this, and you can find it on GitHub. I will also make it available after this webinar. And so this is the first example of a close collaboration between the application and the infrastructure level. And to see at another example, what if we have to distribute load, but also manage state? And for this, there is this recent white paper published by Jonas Bonner, how to build stateful cloud-native services with Akka and Kubernetes. I highly recommend that. The link is on the slide. It really has a great overview of all the options, and so I would really suggest you download and give it a look. But for this webinar, in terms of distributing load and managing state, we'll look at another simpler example, which in fact is my very first journey in the reactive world. In 2013, oh gosh, it's already 6 years ago, boy. Well, I had this small startup with a couple of other people, and our idea was to enable finger gestures across different devices. So you could swipe things from one phone to another or pinch across two screens. And I had one paying customer, which I was very proud of, but clearly wasn't enough to sustain the business. But so here we go. These are a couple of screenshots from back then. You could pinch and make an image appear on the screens where appropriate, at the right resolution, or you could transfer pictures from one phone to another. Probably my favorite, you could swipe objects, in this case, two shapes across from one device to another. And something that makes me really proud, actually, last year in 2018, Nintendo unveiled that this is actually an available feature on the Switch console. So in this screenshot, someone is just swiping across two Switch consoles and to create a battlefield. Or they have this game, it's sort of puzzle where you can compose images by swiping across. So this kind of makes me proud. And Nintendo even patented this thing. And I love that there's a banana on their patent. Well, it tells me that maybe I should have patented it, but it's all right now. So let's go back at our example. How would we go about that? If we imagine an engine, a service in the middle between devices that enables this communication between them, then there's a couple of very important engine requirements here. First, we need to hold state for each device, such as location, which other devices you matched with, or for the third example, who has the shape, which shape do I have? Do I have the square? Do I have the ball? Things like that. And also allow a fast bidirectional channel between paired devices to exchange data. Now, to build this is the reason why I fell in love with reactive system. How would we build an actor-based stateful microservice architecture? There it is. So if we look from left to right, you can see the devices can talk to a listener, a WebSocket listener in our case, and in it there will be an actor that will talk to actors that represent the device and will live on this device service instances. So let's say we have many millions of users concurrently for this service, then we will need many nodes. And in each node, you see on the right, we will have actors that keep state about each device. And when two devices match, like in this image, let's say devices 1 and 3 have matched, then the actors representing those devices will be able to exchange information from one node to another with the concept of actor messaging and location transparency we talked about earlier. So in this case, the logical connection, you can see it like this. Data from the first device, device number 1, will go through the actor device 1, which will pass it on to device 3 actor, which will then push it down to the real device number 3. And in this scheme, that arrow right there between the two instances, it's really core. It's really powerful. And this is something that Akka brings you. Really powerful. In fact, we try to do this with the classic Kubernetes approach, which is stateless microservices. And we try to implement this. Typically, most people using Kubernetes are not aware of tools to build stateful microservices. And so the de facto standard is pushing state down to a distributed database. And we tried go that way, but there were so many reads and so many writes and queries, and scaling would be a lot more complicated, and performance would never top 2 actors running in memory onto different nodes, and it all just felt clunky. without Akka. And this is where Akka really enables you to work with stateful services in a very powerful, elegant way. And well, this was our second case about elasticity. Let's look at some resilience use cases. We have seen how both Akka and Kubernetes deal with resilience, and with that given, we can try and draw a scale of resilience. So let's say on the left side of this picture, we'll have local JVM exceptions. Those are our two friends from earlier. And then as we move towards right, then we get more and more tragedy happening. So we have JVM errors, like out-of-memory error or a stack overflow. And then we'll have hardware failure. And then on the extreme right, we really have some dramatic things happening, such as a meteorite hitting, or one day Skynet will attack him. And so given that, what we can see is that Akka, it's really fabulous at dealing with failures at a JVM level, so inside your own JVM. And where Akka is not able to go, then Kubernetes comes in. So if all else fail and crashes, Kubernetes will notice and restart your pod. Also, if Kubernetes helps you a little with some hardware failure, so let's say like a whole virtual machine crashes, then maybe Kubernetes can do something to restore the pods that were running on that virtual machine, maybe spin them up on another virtual machine or something. But in general, for very big hardware failures or for extreme cases, when Skynet attacks, well, then it really depends on who you're delegating your services to, or in fact yourself, if you're running your own Kubernetes cluster on premise. And so this is another way that we see that Akka and Kubernetes really cooperate fantastically together. And in fact, something that I have heard a lot at my meetup is this idea that, oh, if I have Kubernetes taking care of resilience, I don't need to make efforts to introduce resilience on an application level. I have heard this a surprising number of times. And well, I think there are some very good reasons to take care of resilience at the application level still. And here's a few. First one, obvious, the restarting time of a pod is orders of magnitude slower than an actor. A pod takes seconds to restart, while an actor takes milliseconds. And so that's one. But another one is that because Kubernetes doesn't know what runs inside your containers, the only thing that it can do in case of failure is mercilessly kill that pod and restart it. And these can lead to the dreaded crash loop. If you try to use Kubernetes, I'm sure you've seen this at least once, where a pod crashes, is restarted, and immediately crashes again, and Kubernetes restarts it again in an endless loop. If we take care of this kind of resilience inside our application, then if we have issues, we can choose what to do with it. So as I mentioned earlier, we can have different strategies: restart, stop, or resume. And another important reason is because, again, Kubernetes only works at a pod level of abstraction. The only thing it can do is restart the entire thing without knowing what's going on inside. But why do that if you can only restart the component that failed? Restarting things, it's a costly operation, even with actors, because you might need to restore state, and maybe your state was saved in some persistence layer. So it's a relatively expensive thing to do, and you don't want to have it to do for all the components when maybe only one needed to be fixed. And so we are getting to we're getting. Sure, if you see the slides.
Oop, I think we lost you on the screen share, Fabio.
Oh, coming back.
It's an out of legs exception.
It's an out of screen exception. That's right. Sorry, the second screen went on standby. But here we are. Are we back? Not yet.
No, not quite. The dreaded tone of denial.
Oh, yeah. Sorry about this.
All right.
Are you seeing my screen again now?
Just your background, not the presentation.
Okay, excellent.
There we go. Now we see it.
Should be. Yes, sorry about this out of screen exception.
No worries, thanks.
Well, anyway, we were almost done. We were right at the conclusions. So, main conclusion from this journey we have taken is that application level and infrastructure level really need to cooperate and be tightly integrated with one another. In order to achieve the reactive principles from the Reactive Manifesto, we really need to take care of those principles at both levels. Akka and Kubernetes, yes, both help managing resilience and scalability, but at different levels of granularity. So we really need application and infrastructure level to cooperate. And reasons for the Akka and Kubernetes stack, to me, it's a very powerful stack. Akka has a cloud-native programming model ready to scale from day one. And it enables transparent communication between different nodes of a service, and resilience is built in your service with granular control. While Kubernetes is a great infrastructure choice for your clustered application. And it provides location transparency with cluster formation, helps a lot there, and it introduces resilience at an infrastructure level. So my personal conclusion is that Akka and Kubernetes together give you superpowers. And I would go as far as saying that Kubernetes should be the default deploying strategy for your clustered applications. And for the future, in fact, there's more abstractions and features waiting for you. Akka has abstractions for streaming, for event sourcing and CQRS, reactive streams connectors, and much more. And Kubernetes also has lots more features: storage, confidentiality, rollouts and automatic rollbacks, and much more. And I am always on the lookout for patterns and integration between these two. So please, if you find some interesting patterns about this, get in touch with me. My Twitter handle and my website you have seen them on most slides on the top right. And here are some references of tools and resources that I've used for this webinar, and that was it for my material.
All right, thank you so much, Fabio. This was an excellent presentation. There's actually a lot of questions in here. A lot of questions actually touching on Akka, and I think this would be a great opportunity to get a little understanding from you in your experience as a consultant going into companies where people are maybe just learning about reactive. Akka is a new kid on the block for them. And in terms of how Akka sometimes has the perception that it's got a bit of a steep learning curve, and maybe you could share some advice about what you tell people about learning Akka. What's kind of the payoff for the time they spend learning a different sort of communication paradigm for coding cloud native applications?
Yes, this is a very, very good question and topic. In fact, as you mentioned, learning Akka, even before learning the code syntax, is really about learning a new mindset. But the thing is, to me, there is a reward to that. Because if you think about it, the way that Akka works helps us model the real world much, much better. For instance, the way that actors communicate with each other with asynchronous messaging is a much closer representation of the world. If you think about, let's say you want to know my age, right? You're not gonna have a getter or something in my brain and read my age. No, what you're gonna do is you're gonna send me a message asking, hey Fabio, what's your age? To which I will reply, yeah, my age is 37. So actors talking to each other, to me, that is a great way of modeling the real world, much better than we used to do, 10 years ago with Pojas and classes and all that. And to me, the reward is first in terms of modeling. It just becomes a lot easier to reason about.
Okay. So on the same thread, it might be easy to perceive that when you start working with Akka actors, you somehow need to create, hundreds of actors and do a lot of manual configuration. Is this a bit of a myth, or how easy is it to start being productive with Akka actors just from the start?
So, funny enough, I think the code that I wrote back in 2013 for this device application that I shared with you guys, it's probably somewhere on GitHub still, and I am really ashamed of it if I look at it now, which is probably a healthy thing. It means I've learned something along the way. But in general, the switch to an Akka-based application doesn't have to be entirely traumatic. So if you look at that code, it was sort of plain old Java, but then using actors, and it worked. You could use actor in a bit of a unorthodox way, and like not maybe fully embracing all the potentiality, all the the potential that they offer, and it will still work. So I would say you definitely don't need to have immediately 100 actors out there to appreciate what they can bring to your app. Even only a few actors can maybe simplify part of your app. So it can be an incremental path, let's say.
All right. Still some more questions about actors, this time a little bit more specific. When resilience is maybe the biggest unique benefit of Akka. Just when something crashes, it gets handled, you don't have to worry about it, and it isolates problems before they escalate into something like a big deal.
Right.
When an actor fails, a notification is sent to that actor's supervisor. What happens when that supervisor fails? Is it actors all the way down, or what happens when you get to the very top of the hierarchy with a failure? And is that thing actually a possibility?
Oh, what an excellent question.
Yeah.
Yes.
Congratulations to the young lady who asked that question.
In fact, as I mentioned, the supervisor is an actor itself, which means that it has a supervisor as well. And when I mentioned that there are different strategies to deal with the failure of your children, well, one of those strategies is to actually escalate. So you might want to resume an actor or maybe restart it, but if you don't know how to deal with it, you want to escalate it, which means that the supervisor will keep throwing the failure up in the hierarchy. And so this will be, in fact, the case when there is a JVM error. So let's say one actor has an out-of-memory exception. Well, that is a typical example of a failure that will escalate all the way up. And at the top, there is a sort of God actor, we could call it like that, is provided by Akka, is the actor that creates all other actors. And that actor, well, it will crash the entire system, because an out-of-memory exception is a very bad error. And in fact, this is where Kubernetes comes in, and it will detect that the entire pod has failed and restart it. But yes, in general, to answer the question, there is an entire supervision hierarchy, and so you need to distribute failure handling where appropriate. Yes.
Okay, well, I hope that answers that person's question. Let's talk a little bit about communication and speed. There was a question about whether, can you expect worse performance using a distributed database like Cassandra compared to two actors, potentially persistent actors communicating? But I believe that there's kind of a difference in what we're trying to achieve using Cassandra versus actor-to-actor communication. Could you go over that?
Yes, you also mentioned persistent actors. We didn't really look at them during this talk, but for those who don't know, persistent actors, in a nutshell, they help you implement event sourcing in your application, which means that state of the actor, event by event, is persisted to a database. And so when you want to recover the actual current state, what you will do is you will read all the events one after another in chronological order from your persistence layer, and the evolution of those events is the current state of your actor. So what persistence actors do with the database is really, they read some stuff only when they spin up. And then as things happen, they write, they append a new event on the database, but all the communication between that actor and another actor then can happen via asynchronous actor messaging. And asynchronous actor messaging is extremely fast, because in fact it's just about serialization. Messages that are sent from between two actors on the same JVM are extremely fast, and messages between actors on two different nodes, they need to go on the network, and so you want to serialize those messages as maybe with I don't know, Avro, or you could do JSON, somehow serialize them, and then it depends on the network. But in my experience, any situation like that is faster than writing something to a database, and someone else need to check that database if something has been written and read it. There's a lot more I/O involved and a lot more resources and polling and things like that, whereas actor communication is very straightforward.
Okay, thanks for that. And we've got time for just one more question. And I think this is one I've seen kind of come up a few different times. Excuse the sirens. Fabio, what if Akka and, what if we know that we want to use Kubernetes and Akka is just not on our path right now? We've got a monolith. It seems to be working fine. What happens if we take our monolith and we Dockerize it and throw it into Kubernetes and deploy that to Amazon? What's going to happen? What's the worst case?
Well, so if you're not using Kubernetes, I assume that you are deploying your monolith to some VM, like EC2 instance or something like that. Well, I would encourage to go to Kubernetes, because I was there, and resilience in a virtual machine or elasticity, they can be achieved, but you've probably, I don't know, written lots of scripts, and things can get a bit dirty and confused, and Kubernetes will leverage a lot of that for you. So I would definitely encourage you to go to Kubernetes even without Akka. You will get lots of benefits that Kubernetes alone can give, and your application will probably be a little more reactive. Maybe not all the way, but definitely a gain. What you will lose there is that Kubernetes obviously has abstracted a lot of things for you, so it's hard to be really in control. Kubernetes is in control of your virtual machines, and it decides where pods are spun up or killed, and there's little you can do to control that. So it's a bit of a trade-off in that sense, but yeah, give it a go.
All right. Well, Fabio, thank you so much for taking the time to join us today. This was an excellent presentation. I look forward to getting it published on the Lightbend blog and sharing it with everybody who registered, as well as our excellent attendees. And I think everyone has seen your Twitter handle as well as your website. So look for some invitations to explore Kubernetes from some of our audience, perhaps. And to all of our attendees, thanks very much for joining us today. If you are a customer and you weren't able to get some of your questions answered, go to our customer portal, log in, and you can ask them there. Again, Fabio, thanks so much.
Thank you all very much.
All right. Bye-bye.